All right, everyone, we had some worksheet questions last night for homework. The answers for the worksheet, for all of them, not just the ones that you had for homework last night, but for all of them are up there right now. Take a peek at those for the ones that you were assigned, that is, and let me know if there's any of those questions you'd like to go over. All right, let's take a look at a bunch of these questions here then. Number one, first of all, the normal force on the person in the elevator. Listen, we know what to do for all of these. We know how to start off all of them, right? Everybody knows how to start off all of them. Draw a free body diagram. Okay, if you're not doing that, then shame on you. You need to draw a free body diagram. We know that, so do it. There are two forces that act on this guy in the elevator. What are they? What's one of them? Normal force, which acts up on the guy, right? Doesn't matter where I draw it. I'm going to draw it beside him, although really it's acting on him, right? What's the other force that acts on this guy? Jordan? Gravity. Gravity acts downwards. Now, I wouldn't lose any sleep over this if you drew them the wrong lengths. But by rights, the force of gravity should be longer. Sorry, the force of gravity should be shorter than the normal force in this case. Can anybody tell me how you know that? Before we even do any calculations to determine what the value of the normal force and force of gravity are, we know that the normal force should be bigger than the force of gravity. It's got to be a higher value. How do we know? How do we know that, Tony? Okay, he's riding in an elevator, sure. But sometimes in an elevator, the normal force is actually smaller than the force of gravity. Yeah, because it's accelerating up. It's accelerating up. Let's think about that. If you accelerate upward, then the upward force must be bigger than the downward force. Otherwise, you wouldn't accelerate up. So Fn, since it's the only force that acts up on the guy, has to be bigger than Fg. All right, we know what to do next too, right? F net is equal to the sum of the forces, Fn plus Fg. Ma is equal to Fn plus Fg. So what do we got here? 60 kilograms times the acceleration of 2.00 equals the normal force, which is what we're looking for, plus the force of gravity, which of course is going to be 60 times 9.81, right? All right? Let me give you a little hint here for the future if you haven't picked up on this already. When I say, is that right? And then I repeat that question 3 or 4 times, it's usually not. There's usually something wrong with what I've done if I repeat the question, is that right? 3 or 4 times. Is that right? Is that right? All right. No, it's not right. What's wrong with it? Right. Correct. We need a negative either on the 9.81 or in front of the 60. It doesn't really matter where. Okay, 60 times 2 is 120. 60 times 9.81 is 588.6, but it's negative. It comes over to the other side by adding, so it becomes 120 plus 588.6, which ends up giving you a normal force of 709 newtons. So gravity is 588. Normal force is 709. That's exactly what we predicted, right? We predicted the normal force would be bigger than the force of gravity. It's got to be if you accelerate upwards. Do you remember we said when we defined a normal force, we defined it as that force of the ground pushing up, in quotation marks, up at 90 degrees? We also said that the normal force was your apparent weight, how heavy you feel. You ever notice this when you're in an elevator? Especially an elevator in a tall building, like say the CN Tower. And you start accelerating upwards. Do you ever feel like you're being pushed down on the floor? Do you ever feel like you're heavier for a brief moment? That's because the normal force is bigger than the force of gravity, right? You're used to feeling, say, 588 newtons for gravity. But for a brief time, as you accelerate upwards, you're experiencing 709 newtons. You feel heavier than what you really are. Okay, 2. What's the force of the floor pushing up on the person in the elevator? This is the same question, isn't it? The force of the floor, the normal force. This time we have a normal force acting up. We have a force of gravity acting down. Is gravity going to be bigger or smaller than the normal force here? Bigger or smaller than the normal force? It's going to be bigger. How do you know that? Good. The acceleration is downwards, so the downward force has to be bigger than the upward force. So we're going to set it up the same way. F net is equal to the sum of the forces, Fn plus Fg. We should find, when we go to do our calculation here, that Fn is a smaller number than Fg. We'll see in a minute here. Mass is 50. Acceleration is -2. Fn is what we're looking for, the force of the floor, or the normal force, plus 50 times 9.81. Is that right? Is that right, Lewis? That's right. Good. Negative 9.81. Or stick the negative out in front. It doesn't matter. So this gives me negative 100 on the left-hand side. This goes over to the right-hand side. This is negative 490. It goes over to the the left-hand side by adding, because there's a negative number over here. And when we solve for Fn, here, it works out to be 391 newtons. So gravity was 490. Fn is 391, which is in that ballpark that we predicted, right? We said that the normal force would be smaller than the force of gravity. You guys ever notice this? When you're in a tall building and the elevator starts going downwards from the top floor, you feel like your stomach is sometimes in your throat for just a brief moment? Do you feel lighter? Like you're being lifted up off of the floor? Yeah, you should feel lighter, because the normal force, that is your apparent weight, how heavy you feel, is less than gravity, which is what you usually feel. How many people have ever been up the CN Tower in Toronto? Nobody in this room besides me has been up the CN Tower? You guys got to get out a little bit here. Used to be, up until like a year ago, literally the world's tallest structure, man-made structure. The world's tallest freestanding structure. Now it's not anymore, but I forget how tall it is, but it's crazy high. And then you ride up an elevator up to the top of the CN Tower in a glass elevator, so you can see it over the city as you accelerate in this high-speed elevator. It's pretty neat. But you really notice in a building like the CN Tower, because it's so high and the elevator needs to move so fast and accelerate so quickly at the start and at the end, you really notice those changes in weight. Like you really notice that you feel heavier at the beginning and you feel lighter at the beginning when you accelerate downwards. Okay? You notice that a lot more than you do in like a 3-story doctor's office building in downtown Okotoks kind of thing, because it accelerates a lot quicker. Hey, I didn't ask you to do number 3, so we won't go through this in a whole lot of detail yet. I'm going to assign the rest of that here today, but I will just draw your attention to it just for a second here. What are we asking for in question number 3? Calculate the apparent weight of the person in the elevator. What are we really asking for there? Yeah. No, not the mass. Yeah, the normal force. Okay, same as we have in the first 2 questions. We're asking for the normal force. Apparent weight is how heavy you feel. Okay, that's going to be your normal force. Now, it says it's moving at a constant velocity of 3 meters per second square, 3 meters per second upwards. We don't have anywhere in this equation where we see velocity, but we do have somewhere where we see acceleration. What's the value of the acceleration if you're traveling at a constant velocity? Okay? Nope. 0. If it's a constant velocity, the acceleration is 0. So the fact that it's 3 meters per second is completely irrelevant. It could move up at 20 meters per second. If it's a constant speed, nothing's going to change. Okay. So I'll leave you with that one to do tonight. All right, we had 5, 6, and 7 I think you need to go over. Is that right? Straighten it out here a little bit. We got a 5-kilogram object, we got a 2-kilogram object, and there's a force of gravity acting on the 5-kilogram object. Really, it's downwards, but I like to draw it horizontally here. Just, to me, makes it a little bit easier. That force of gravity is going to be 5 times 9.81, which is 49.05 newtons. There is a force acting downward on the 2-kilogram object, that's gravity. There's a normal force acting up on the 2-kilogram object. They cancel, so even if you don't even draw those in, that's okay. We should by rights, but it's not the end of the world since they cancel each other out. The only force we have acting here that doesn't cancel is the force of gravity. So we're going to say F net is equal to the sum of the forces, which is just Fg. MA is equal to 49.05. And M is going to be 7, right? We use the total mass here, 7 kilograms times the acceleration equals 49.05. 49.05 divided by 7 ends up giving me 7.01 meters per second squared for the acceleration. 6 and 7 are both real similar to number 5, but they both involve just a little bit more. 6 has a force of gravity. Let's label those 1, 2, and 3. 6 has a force of gravity acting on number 1. 7 has a force of gravity acting on number 3, both downwards. If we stretch that out like this, a little bit easier to see that these two forces oppose each other, and that one's going to be positive and one's going to be negative. F1 is going to be 5 times 9.81, 49.05. F3 is going to be 7 times 9.81, which is 68.86. Is that right? Somebody check that. 7 times 9.81. I think that's what it is. 6, 7? Thank you. Now, of course, we do the same thing as we always do. F net is equal to the sum of the forces, where it's just F1 and F3. What mass do we use? 5, 3, 7, or some sort of combination of those three numbers? Stephanie? Yeah. Going back to the last question just for a second, Stephanie here. Why wouldn't this one be a negative? With the way that I have it drawn here in my diagram, it's to the right. Really, it's a downward force, and because of that, you can make it negative if you want to. But with the way that I've set up my sign convention relative to the diagram that I've drawn here, I've got it drawn to the right. So I'm going to make it positive. If you draw your free body diagram a little bit differently, though, or you define right as negative, that's okay too. No, not unless you're told there's a force of friction, no. We know nothing about friction in either of these questions, 5 or 6, so can't do anything about that. 7 we do, but right, because we're told there's one there. What mass do I use here, guys? 5, 3, 7, or a combination? 15. I use the combination of them, right? The total mass is being accelerated, so let's use that 15. 15 times A is equal to negative 49.05. We're making that negative, plus F3, which is positive 68.67. Stephanie, your question kind of arises here again, right? The one that you had for the last question here. We're making 49 negative. Why? Well, it's a downward force. We're making 68 positive. Why? Well, it's a downward force as well, but they oppose each other. One of them's got to be negative, one of them's got to be positive. We can make whichever one we want, negative and positive, but I'm just choosing to follow the sign conventions relative to the diagram that I drew here, which shows the 49 to the left and the 68 to the right. So it's easiest just for me to make that one negative and that one positive. Same as up here, right? It was easy for me to make that one positive because it was drawn to the right, even though it's not really to the right. All right, add these together, divide by 15, and we get an acceleration there of 1.3 meters per second squared. Good? All right, let's take a look at number 7. Number 7, if we take the 2 kilogram object, put it right there, the 6 kilogram object, put it right there, well, there's a force of gravity acting on the 6 kilogram object. It would be downwards, really, but we'll draw it to the right. There's gravity and a normal force acting on the 2 kilogram object, but they cancel. Where are we going to draw friction? I'm just going to erase these, actually, so it doesn't look so cluttered. Where are we going to draw friction, Lewis? Good. If it's moving to the right, and it will because of gravity, then we're going to draw friction to the left. So friction is going to act this way, and it has a value of 20 newtons. So there were a couple other forces that canceled each other, the normal force and gravity on the 2 kilogram object, but these are the only two that don't cancel. So let's say, next step, F net is equal to FF plus FG. They all start becoming the same, don't they? They sure seem like they become the same question here almost. Right? We just draw the diagram, F net is the sum of the forces, and so on. Okay, well, what's the mass that we use there? 8, good. The total mass, because the total mass is being accelerated, good. Force of friction, we're going to make negative 20. And the force of gravity, we're going to make 6 times 9.81, which was 58 point, I don't have that written down on mine, 58.86. 58.86 newtons. Negative 20, positive 58. We're making gravity positive here because we've got it drawn to the right, even though it's really downwards. So 58 subtract 20 divided by 8 ends up giving me 4.9 meters per second squared. Finally, we had 11 and 12 that we wanted to go over here. Both of these are what we in physics call inclined plane problems, but what we in everyday life would call hills. So we've got 2 hills here, both angled 30 degrees. That's good because 30 degrees makes the math a little bit easier. Both of them experience the following 2 forces. Gravity acting down, straight down, and the normal force acting perpendicular to the surface, right like that. Then there's a force that joins the 2 together, which is really the combination of the normal force and the force of gravity. We call that F parallel. F parallel is 90 degrees to the normal force, always. Now, the angle that we're going to find in here is going to be the same as the angle of the hill, so it's going to be 30 degrees. We'll do that for both of these diagrams, for 11 and 12. Gravity straight down, normal force at 90 degrees. F parallel, you could draw it in 2 places. It's the sum of Fn and Fg, but we can draw it as being the force that brings this object down the hill as well. Well, when I go to set this up, I'm going to say F net for number 11 is equal to the sum of the forces. What sum of the forces do I want to put in here? Is it going to be F parallel plus Fg plus Fn plus F parallel plus Ff? Or what? Okay. Okay, so F parallel plus, not F gravity, no. Yeah, whatever that force is, or I'm actually going to call it Fa because it's meant to represent not friction, but somebody pulling it up the hill, but it doesn't really matter. Can somebody answer this question for me? Somebody else, please. Why did Carey leave out Fg and Fn? Why did Carey leave out those 2 forces? Tony? Good. We've already included those. F parallel already includes Fg and Fn. Right? It's the sum of Fg and Fn. Well, we got to get F parallel, right? So let's do that over here. Let's say sine 30 degrees is equal to opposite, that's F parallel, over the hypotenuse, which is m times g, 5 times 9.81. So F parallel is going to be equal to 5 times 9.81 is 49.05. Sine 30 is 24.525. Thank you. So now we plug them in here. We got a mass of 5 times acceleration. F parallel is negative 24.525. Why negative? Why did I make that negative? Derek? Yeah, going down the hill. We're going to make Fa positive 15 newtons. Now, you could have switched that around, right? You could have made it positive 24 and negative 15. That would be okay. They both just have to be opposite signs there. Now, it's not so bad, right? About negative 9 on the right-hand side divided by 5. Do the math on that one on number 11. And we end up getting negative 1.9 meters per second squared. And finally, our last one here. Calculate the force of friction. We know there's friction here. Let's draw friction in this diagram. We don't have it drawn yet. Let's include it. Which way is it going to act? Seth, which way is friction going to act in question number 12? Down the hill or up the hill? What do you think? You tell me whether the object's moving up or down. Good. Friction's acting up because the object is going to move down the hill, right? Okay, so let's set it up. F net is equal to F parallel plus FF. We're solving for a different variable here than we usually solve for, right? We almost always solve for acceleration. This time we're solving for the value of the force of friction. F net is m times a. It's 5 times 9.81. No, it's not. It's 5 times what? See, we all make mistakes. Negative 9.81? Nope. Negative 3. Right, 3 because it's not looking for gravity. We're looking for the acceleration of the system. We're going to make it negative because it's down the hill. F parallel, we can figure that out as well. It's the same value, isn't it? Same value as it was in the last question, so let's not do it again. We're going to make it negative 24.525 plus FF. So get this number, it becomes negative 15 on the left side. Let's take the 24 over by adding because it's negative on the right-hand side. And it becomes, FF becomes positive 9.5 newtons. We should expect it to be a positive value, right? Because somebody said, who was it that said it was up the hill? I asked which direction friction was, and somebody told me, Seth. Seth told me it was up the hill, right? Well, we should get a positive force of friction then if it's up the hill. Good? Okay, here's your homework for the weekend. The rest of this worksheet. Okay, the rest of this worksheet. We have 3 and 4 on first page we have to do. We have 7, 8, 9 on the second page. And we have 13 and 14 on the third page. I'm not asking you yet to do the back side of the page. The back side of page 4, 15, 16, 17. Don't worry about that yet. In addition, that's going to be your only real homework for the weekend. But in addition to these official homework questions, these doable homework questions, I'm going to put a question on the board for you in just a moment. It's meant to be a challenge question, a real challenge question. Anybody that likes to be challenged, I want you to give it a try. If you don't have it done on Monday, I'm not going to zing you for homework. Okay? But if you like a challenge, if you want to exercise your brain, I'm going to ask you to give it a try. Give it a legitimate try. Usually what happens when I give this question, I give it every year. Usually what happens is I get either 0 or 1, maybe 2 people that actually get this question. Okay, most people don't. It's a tough question. Okay, if you want to be the smartest person in this class, okay, HTA's smartest person, and I want you to give this question a try. Right, we'll put it up in just a couple minutes. For now, I want you to work on the rest of these questions on the worksheet. All right, everyone have a look up here. The challenge question, the bonus question. Tell you what, anybody who gets this question completely correct gets their lowest quiz dropped. The lowest quiz of the year, we'll just scratch it off because you deserve not to have a bad quiz mark if you get this question right. So here's what it is, right now at least. There's more. We've got a 30-degree incline here on this hill. We've got a 500 kilogram object on this hill. We've got a coefficient of static friction of 0.2, coefficient of kinetic friction of 0.1. We're not sure if it's going to move yet, so we're going to have to figure out whether it moves. Okay. We've got a pulley up here that joins together 2 masses. The first mass is 500 kilograms. The second mass, well, the box is 80 kilograms. The guy inside the box is another 50 kilograms. So far, so good? Oh, I think this is hard? Wait. The guy inside the box is holding a ball. And after 4 seconds, so this is released, okay? So let go. After it's allowed to move for 4 seconds, the ball is thrown. The ball is thrown at 20 meters per second relative to the elevator at an angle of 30 degrees. The question is, how far does the ball go? Wouldn't that be like a great question for a final exam? Like you got one question on your final exam. It's projectile motion, it's pulleys, it's inclined planes, hills, it's pretty much everything we've done this year, isn't it? All in one question. Who's excited now? All right, right now I'd like you to work on your worksheet, guys. If you want to start working on this one now as opposed to your worksheet, that's okay. But your worksheet needs to be done for Monday. This, I'd love if you gave it a try for Monday, but we're not going to lose any sleep over this one if you don't get it done or you don't get it correct. Okay, the worksheet's the real important one. This is the challenge one for the people that really want to be challenged.